Thank you. So I'll be saying an announcement out about that first Mobius assignment in the next, hopefully this afternoon. And I would not take I think this is going to be an easier assignment than the other ones because again, we're trying to work that things out. So I'm not spending a lot of time developing nasty, evil questions. I'll spend that doing it next week. So we're going to go with that. So that, yeah, again, that goes live 12:30 or 12 noon tomorrow. And then it's going to be live till Friday night at midnight. Okay, so I'm going to continue with where we're at here. And where we left off last class is we just started talking about, we're going to start talking about functional groups, and we dropped off because we ran out of time, which is how things work. All my lectures are really designed for an 1.5-hour period, and then this hour just really throws me, and yeah. Okay, so types of hydrocarbons. So type 1 of the hydrocarbons. Hydrocarbons are exactly what they say they are. They are made up of hydrogens and carbons, so they're hydrocarbons. And the major classes are alkanes, alkenes, alkynes, and aromatics. And they're named, something is named after the most double bonds it has in one group. And so something is an alkene if it's got a double bond, something's an alkyne if it has a molecule with 3 double bonds, or a bond with 3 double bonds. Oh, that's awful. You should be ashamed of yourself. The nice thing is the chat window, we can automatically take marks off for for really bad puns. Okay, so again, you guys all know this stuff. We don't need to go through this in a lot of detail. Alkanes, carbon hydrogen single bonds defines everything. They come in different shapes. They can be branched, they can be linear, they can be cyclic. Alkenes contain carbon double bonds. A lot of stuff actually coming out of the ground is an alkene. A lot of the oils are alkenes, and we crack them. And so we also use them a lot for a lot of polymer bases. So most of the plastics that well, I'm currently wearing a fleece, which probably is mostly polyester. Strange enough, polyester is not based on alkene, but this is probably polyethylene or my pen. I don't have my camera on. Turn my camera on. So a lot of plastic around me is probably polyethylene or polyvinyl chloride, and those are all alkene-derived materials. And I'm going to minimize my window because this is going to be in my way. There we go. And then alkynes contain carbon-carbon triple bonds. So if you have a molecule that has both a carbon-carbon triple bond and a carbon-carbon double bond, and you're told to define the class of molecule, it will be an alkyne. If you were talking about the specific functional groups, you would call the triple bond the alkyne and double bond an alkene. I will also use the term olefin for double bonds. I will try not to use the term olefin, but I will use the term olefin because I know myself, and it's an archaic terminology for double bond. And it refers more to the functional group rather than the molecule as a whole. So an alkene can refer to a molecule as a whole, and olefin refers to the carbon-carbon double bond. Yeah. So aromatics are special double bonds. The next course actually is all about aromatic molecules, and they're not called aromatics because they smell good. Actually, they might be called aromatics because they smell good, but that isn't what defines them. What defines them is this arrangement of double bonds, and what's really special about them is that they have a resonance structure that is identical in energy to themselves. And so when you try and draw this thing out using a linear combination of atomic orbitals, like we were doing last class, you're going to have each of those carbons as a p orbital. Each of those p orbitals has a single electron in it, and it can make a double bond with either the p orbital to its left or the p orbital to its right. And so it's kind of always making double bonds with both, because that's the way it's a molecular orbital, and we're not really localizing that double bond. It's more that we have these electrons equally spaced between all those carbons. The electrons flow really well in there. They're constantly moving, and if you disrupt that, then you lose activity. The Mobius assignment isn't available yet. It goes live tomorrow at noon. But if you log into Mobius, you should now see it in your calendar. And it's also going to be the top thing on the left, right after introductory material. So if you played it all with Mobius yet, you should be able to see that there is something there, but you won't be able to access it. You know what? Maybe I'll screen share at the end of class and add to the end of the thing. Stuff that isn't directly related to lecture, I can add this. I've already said it 3 times. I'm not going to tell you the due date again. I've just been saying it endlessly. So the next class of heteroatoms, of functional groups, are those that involve heteroatoms, so things that aren't carbon and hydrogen. Could somebody please answer, Aya? Yes, thank you, Nicole. Yeah, perfect. Okay, so we have alcohols. Alcohols are any molecule that contains a single OH group attached to a carbon that isn't attached to other oxygens. Normally when we're talking about functional groups, what we're talking about is the carbon and the thing attached to it. So this is kind of the functional group. It includes the carbon and it includes these other atoms that are kind of associated with that, the hydrogens and the OH. So we have this terminology here where I'm going to call, so we have different types of alcohols here. And we're going to come into this, and I just want to make sure everyone's seen this. This would be called a primary alcohol. It's primary because the carbon that is attached to the oxygen attached to only one carbon. This doesn't actually have a name, it's just a methyl alcohol because the carbon is not attached to any carbons. It's kind of like a 0th degree alcohol. This one we would call a secondary alcohol. Because the carbon is attached to 2 carbons. Notice I'm only counting carbons. I don't care what other atoms it's attached to. I'm only counting carbons. I guess silicons would count too, but that's silly. We're not going to see it in this course. Then we can have a tertiary alcohol. Where the carbon is attached to 3 carbons. You can't have an alcohol where the carbon is attached to 4 carbons because that would mean your carbon's making 5 bonds and your carbon can't make 5 bonds. So these alcohols all react differently. A primary alcohol reacts like other primary alcohols. So you can expect ethanol and propanol to have similar reactivity. Where do these things show up? Well, you can use them for fuel. Importantly, you can use them for beverages. And because of that OH bond, the OH functionality, they can make hydrogen bonds and they can accept hydrogen bonds. Because the hydrogen attached to the oxygen can be shared with another heteroatom through a hydrogen bond, and the oxygen's lone pairs can interact with other hydrogens to form a hydrogen bond. If you don't have a hydrogen, you have a carbon, that's an ether, 2 alkyl groups bonded to an oxygen. An alkyl group is just a carbon chain. Any carbon chain. And because of that oxygen, they are more polar than a standard hydrocarbon. You have a dipole moment. The oxygen is going to be pulling electrons towards it away from the carbons. But they can't form any hydrogen bonds with themselves because they have no hydrogen bond donor. They can accept hydrogen bonds. You stick an ether and an alcohol together. The ether oxygen can interact with the alcohol hydrogen. Nothing wrong with that. But an ether can't react with itself through a hydrogen bond because there's no H attached to the O. They're useful solvents. We'll actually still find them in solvents. They used to be anesthetics. Somebody's asking what's the difference between R and R prime. R is alkyl chain. So if I had O, R, R, R equals R. It has to, because it's the same thing. But R does not equal R prime. So I can indicate that I have two different things. I'm not defining what they are. They're alkyl chains, but they're different. So an R prime says it is an alkyl chain. An R is an alkyl chain. R prime is a different alkyl chain. And R double prime is a different alkyl chain. Sometimes you see people using Roman numerals for this or Arabic numerals. I like Arabic numerals. You go up to like R12 and stuff when you have 12 different R groups attached to a molecule and you're trying to patent something and you're trying to protect everything in that space. Ketones and aldehydes are carbons double bonded to oxygen. So alcohols are carbon single bonded to oxygen. Ethers are carbon single bonded to the oxygen single bond to two carbons. A ketone is this functional group. This is a carbonyl. C double bond O, just like C double bond C is an olefin, C double bond O is a carbonyl. So a ketone is a secondary carbonyl. It is a carbonyl where the carbon is attached to two other carbons. An aldehyde is a primary carbonyl, where the carbon is only attached to one other carbon and is attached to a hydrogen. Terminal also. It's at the end of a carbon. That says terminal. I promise. Sort of. So where the carbon's at the end of the carbon chain. Yeah, if it's on a side, it's an aldehyde. That's actually quite clever. They smell good. That's mainly what they do. They smell good. They actually do an awful lot of chemistry, so it's a lot more than that. But not much more to say about those. We're going to talk a lot about their chemistry. Actually, we're not. We're not going to talk a lot about their chemistry in this course. You're going to learn a lot about their chemistry in the next course and the course after that. Carboxylic acids are carbons that have 3 bonds to oxygen. You can see a trend here. We had 2 bonds to oxygen, 1 bond to oxygen. Now we're 3 bonds to oxygen. They are mildly acidic. pK is about 5. Acetic acid is 4.89. It's still stuck in my head from my Gen Chem course way back in the 20th century almost. And they interact with water to dissociate like acids. You've seen lots of that. Acids tend to stink, actually. Like they're kind of, the acetic acid is not that bad. You think vinegar stinks, it doesn't. Some of these longer ones really reek. They're pretty disgusting. Not like aldehydes and ketones, which generally actually smell kind of sweet and pretty good. I have no idea what my mouse is right now. Let's see what happens. Then we have the carboxylic acid derivatives. The ones that we need to be familiar with are the acid chlorides, the esters, the amides. And here are some examples. You are responsible for naming acid chlorides, esters, and amides, as well as acids. You're responsible for being able to name everything that we see in this presentation today. I'm not going to give you complex esters or amides to name because they get kind of funky and the naming gets really stupid. But simple ones you will run into. Finally, then we run into the amines. Amines are carbons attached to nitrogen. They're alkylated derivatives of ammonia. Again, where you remember ammonia is NH3, so replace one of the hydrogens with a carbon, you got an amine. We're going to come back to both of these terms, that they are basic, they are nucleophilic, and we're going to define what those mean, and they can hydrogen bond. Again, they have NH bonds. Of course, they can hydrogen bond. They've got a lone pair. They can interact with things. Again, like alcohols, we have this primary, secondary, tertiary amine. Except in the case of alcohols, we were talking about the carbon attached to the alcohol, the oxygen. Here, we're going to talk about the nitrogen itself. So methylamine is a primary amine. Ethylamine is a secondary amine. It's got 2 carbons attached to the nitrogen. Triethylamine is a tertiary amine. And I'm really sorry that we are not consistent with how we use the terms primary, secondary, and tertiary. But we're talking about the most important thing we need to worry about with these molecules. And with oxygen, it's like you're either an alcohol, water, or an ether, depending on how many carbons you're attached, versus hydrogens. Nitrogen gets more complicated. These are special names. So no, these are not IUPAC names. These are non-specific names. So no, you do not need to be able to name those. I'm gonna keep the naming relatively straightforward. You're not gonna have anything too funky. It's gonna be long, like carbon chains with branches off of it. Really nothing that you haven't seen probably in high school, with the exception that we're gonna add stereochemistry to it, which some of you might have seen in high school. And then the last of these functional groups that's to do with nitrogen, well, it's not the last one, we've got a few more that we're going to talk about, are the amides. They're a combination of a carboxylic acid with an amine or ammonia, where you replace the oxygen with a nitrogen, you get an amide instead of an amine. Or if you're British, you call them amides, but they're weird. And so I'm going back to amide. They're not basic like ammonia because of the resonance, because the lone pair of the nitrogen is kind of tied up with the carbonyl. So you got resonance going on. So you don't have like a free lone pair in the same way you do with an amine. That resonance tied up. Okay. And then we have nitriles. So nitriles are C triple bond N. They're basically cyanide groups. We can name them like this. If we have a molecule, let's say we had a molecule like this. I'm just going to draw a molecule. I didn't mention the halogens, but they're there too. Okay. Because I felt like it. And I want to do something else. Okay. So let's say that's my molecule I've drawn, and I ask you to name that. Now you have to dig deep into your memories of high school. But I'm going to give everyone a few seconds, 20 seconds to think about that, and we'll talk about how we can go about naming something like this. Again, if you need to revisit the rules on naming, they are in the textbook. I'm not going to go over them in this class. No, I want to go back up. I want my mouse. There we go. Oh, I saw it for a second. Okay. So if anyone's gotten a chance to look at this, you're going to, okay. So the first thing you need, okay, there's lots of first things you can do. I don't really care. I think the first thing you should try and do is identify what your main chain is. So your main chain should be your longest chain that counts. Yeah, count the carbons. Should be the longest chain that contains your core functional group. So, okay, so what's my core functional group? What is the most important functional group on this molecule? What is going to dominate the naming? And the general rule of thumb, because I have no idea why this is the rule, the carbon that makes the most bonds to oxygen is your most important carbon. That's going to be carbon number 1. Carboxylic acid. The carboxylic acid must be in the core name of the molecule. Then I can count along my carbon chain in order. I have a chance to branch here. I could count this as carbon 5, but then my chain ends. This chain is obviously longer. Carbon 5, carbon 6. My favorite kind of trick is I continue the zigzag. I can bet that some people go carbon 7, carbon 8, but that's incorrect because this chain is longer. So that's cool. Now we need to identify what we have. We have an oic acid as a functional group. That's this guy here. I want more different colors. I want like hot pink. Okay, I'm not going to get hot pink. I'll go with green. We've got a 3-hydroxy. We've got a 4-cyano. It's tempting. Nitriles are called cyano groups. We have a 5-chloro. That looks weird, but I think I spelled it right. We have a 6-ethyl. There's an ethyl chain off of that. And we have an 8-keto or oxo. I'm okay with either. A UPAC is oxo, but keto gets used. And I like keto because it keeps my aldehyde, my ketones in place. So if we're naming this, then we have to follow, and it's a nonane is the base name. So what I've done there is I put all my pieces together. I've written them all out. Now I just need to put them in order. And now the order we'll put them in is we put them in alphabetical order. So this molecule would be 5-chloro, 4-cyano, because H comes before Y, 6-ethyl, 3-hydroxy, 8-oxo, non-noic acid. Non-noic acid. I'll accept non-noic acid as well. That's your ethyl group right there, because there's an ethyl group attached to it. That's a good point. Doesn't need to be a dash. It's perfectly acceptable to just run that together. That probably is better. I'd accept a dash. It helps keep things separate. Punctuation's nice, but you don't need it. As somebody was pointing out, you should have dashes between letters and numbers and commas between numbers. We don't have multiple of the same thing in this here at all. I'm fine with 8-oxo non-noic acid. There's lots of, you could stick some of these names into that final term if you like. That looks like arid, but it's acid. Yeah, I'd accept 8-keto. Yeah. Okay. So where we started with was like dissolves like. Why 4 then 6? Yeah, but you don't need to with the acids. The acids are the one thing you do not need to put a number on because they're always at 1. Because they can't not be. Aldehydes are the same things. Aldehydes are almost always at 1. And it would be not nan, it would be non. Chloro is first because it's alphabetical. Yeah, cyanose and nitrile. Yeah. So if any of this, no, I named it alphabetically. What if there was an aldehyde on the other side? Then you would still have the acid as the number one, and it would be 8,9-dioxo because of the two carbonyls. We're going to do actually some alkenes and alkynes in a bit with E and Z. So I'm going to leave that off for now. I think you guys have seen a lot of this, so I don't need to review this as much. But if it is freaking you out, that's what the naming game is for. Go play the naming game. I'm kind of leaving this to a trusting that you're all, mature students who can take responsibility of their own learning. So, okay. What I really want to emphasize here is functional groups do drive reactivity. Carbon-carbon bonds and carbon-hydrogen bonds tend to be kind of boring. That's not actually true, but for the purpose of this course, it's true. Okay, so I'm going to switch over. Man, it still took 20 minutes. Oh, okay. That's awful. I get to look at myself for a minute. What the fuck did I do? Good. Oops. So now the Ogilvy book decides to put acids and bases in chapter 5. So we are jumping ahead to chapter 5, and we'll come back. So what we're going to do is we're going to review the different definitions of acids and bases. We're going to review pKa, conjugate acids and bases. And then this is the most important, I think this is the most important lecture of the course. We're going to outline structural effects on acidity and use these to predict the relative acidity of molecules. And I actually think this underlies everything else that we're going to do, because everything that applies to acidity applies to everything else as well. Finished by defining Lewis acids and bases and defining nucleophiles and electrophiles, and of course this is going to spill over to next class. By the way, tomorrow's assignment ends at that hydrocarbon lecture thing that I just gave. We're not going to have anything on tomorrow's assignment from this. So the first definition was Arrhenius acids. This defines an acid as something that dissociates in water to give H3O plus ions. Well, releases H plus in water, depending on, I don't think Arrhenius actually discussed hydronium, which is H3O plus, but kind of the modern version of Arrhenius's definition. Stronger acids dissociate to a great extent. So sulfuric acid is a strong acid, completely dissociates in water. Acetic acid is a weak acid. It does not completely dissociate in water. Okay. This is a really boring definition. Arrhenius bases are things that dissociate in water to give hydroxide ions. So a strong base like sodium hydroxide, a weaker base is magnesium hydroxide. It does not completely dissociate in water. Again, this is a really boring definition. It's actually a much worse definition in the H+, because all sorts of things are really basic, whereas often, thinking about H+ being an acid is still a pretty good way to think about it, though we're going to talk about how that's wrong. So acidity and basicity of solutions. I don't know how much of your life last year you spent on these equations, probably way too much, but the Kw of water is 10 to the minus 14. That is the concentration of acid times the concentration of hydroxide times the concentration of hydronium. Neutral water has equal concentrations of both. They're both 10 to the minus 7, which is very, very small. If your hydronium concentration goes up, your hydroxide concentration goes down, and you're acidic. And if your hydronium concentration goes down, your hydroxide concentration goes up, and you're basic. We use the pH scale to define this. So neutral pH is 7 in water. Anything more acidic. Any pH lower than that is acidic. Any pH higher than that is basic. Okay, so the Bronsted definition is quite. I left off the umlaut on Bronsted's name. So the Bronsted-Lowry definition is a bit more non-specific. It actually doesn't really change anything from the Arrhenius definition in terms of acids. So Bronsted acids tend to be Arrhenius acids. Bronsted bases, though, could be quite different. And so what we're saying here is anything that can donate a proton is an acid. Anything that can accept a proton is a base. And so what we're talking about here is the movement of protons. So we have two examples here. Sodium hydroxide is both an Arrhenius and a Bronsted base. HCl is both an Arrhenius and a Bronsted acid. And you get sodium chloride to water. And again, if anyone's unfamiliar with this, I just saw a comment on conjugate. I think I missed some part of the conversation. I don't know where I put the chat window. There it is. I have two pictures of myself because I'm a narcissist. It's because I actually have two computers logged in on here at the same time. So I've got one computer with my tablet and one computer that I'm using with the microphone because my tablet's microphone is garbage. So, yeah, and again, if you're talking about conjugate bases and conjugate acids, water is the conjugate acid of sodium hydroxide. Water is the conjugate base of hydronium. Sodium chloride is the conjugate base of hydrogen chloride. Hydrogen chloride is conjugate acid of sodium chloride. Conjugate acids and conjugate bases are always relative terms. You're always the conjugate base of something. You're not just a conjugate base. Yeah, water is both an acid and a base. Most things are both acids and bases if you try hard enough. So sulfuric acid here is a very strong proton donor. It is an Arrhenius acid. Ammonia is not an Arrhenius base. It does not dissociate in water to give hydroxide. But it is a proton acceptor. It is a Bronsted base. And so here it is being a Bronsted base. Yes. You can tell I know exactly what's coming up in my next slide because I just talked about this. Yeah. So acid strength, there's a few different ways to measure acid strength. In water, the Ka works well and the pKa works really well. Things get a little bit more complicated when we move out of water, and we're going to be doing a lot of moving out of water. But in general, if you have a handy little pKa table next to you, which you will because it's open book, I won't be asking the pKa of anything, obviously. So a strong acid generally is defined as a molecule which has a pK under 0, that provides a pK under 0. Things like sulfuric acid, very strong. Weak acids, generally above 4. And then you got the wacky space in between where you have sort of, maybe kind of, sort of strong acids. I don't think you've seen a lot of them, but they're kind of activated carboxylic acids mostly in that space. Something should be happening when I'm clicking. There we go. So this is a pretty standard pKa table. I used to always throw this in on every exam. You can, if you really want, there's a pKa table online called Bodwell's pKa table. I think it's probably got like 100,000 things on it, different types of functional groups. Probably overkill. This is probably a better way to go. So as you go up, you get stronger acids. As you go down, you get stronger bases, with the conjugate base being a stronger base. So amongst some of the stronger acids out there, it is definitely not the strongest acid. They come a whole lot stronger than this, are the acid halides. So things like HCl. And again, if we remember, and HI is even stronger, and HBr is strong. So these are very strong acids. Down amongst the strongest bases, we've got, you actually don't get, you do get stronger than methyl minus, but not humongously stronger. The pKa of the methyl proton is 40, over 40. So you need a really, 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 really strong base to strip off that proton. This is not acidic. Whereas HCl, the pK of the hydrogen on HCl is minus 2.2. That just comes off like that all the time. It's just always coming off. So base strength is inversely proportional to acid strength by definition. So a strong acid creates a weak base. A weak acid creates a stronger base. I don't really like strong. I think for methoxide, I'm happy with stronger. So I'm going to talk a lot about happy and unhappy charges. And looking at these two molecules here, you cannot know anything about whether they are a strong acid or a weak acid. You might know that because you know that HCl is a strong acid, but you can't predict that HCl is a strong acid based on the information of HCl. You can predict that methoxide is a stronger base than chloride based on this information, looking at the charged species. And that's because Cl- is happy, O- is not happy, or it's less happy. And so chloride is perfectly happy sitting around as negative charge indefinitely. O- is not. It wants a proton badly. And so I'm going to talk a lot about happiness. PKB is a thing that exists. We are not going to refer to it again. I don't know anybody who has ever used PKB for anything useful. I don't know why we discuss it. It's confusing. We are going to stick to pKa's. I am not going to mention that PKBs exist for the rest of this course. So there's a slide saying it exists. Okay, so here's kind of the core of what we need to think about. Predicting equilibria. So which way does an equilibrium lie? Let's say we have two molecules. There's a sodium floating around, but we're not going to ignore it because it's a spectator ion. Okay. So the way I would phrase this question, and I guarantee you there's going to be a question on the exam along these lines because I love this frequent question, is I could phrase this multiple ways, but in the end, I'd probably fall back on exactly what's on this slide here. Which way does the equilibrium lie? I've drawn an equilibrium arrow between two sides, and I've drawn it even. It is not even. This is not a 50-50 mixture. So now I wouldn't ask this question because you would flip back to your handy little pKa table and you go, oh, this is easy. If I can interpret a pKa table properly. The acid is more acidic than the alcohol. And so since the acid is more acidic than the alcohol, this is a stronger acid. That is a weaker acid. Strong, weak. And what that means is the conjugate base is strong and the conjugate base is weak. And that makes it pretty easy. You don't want a strong acid and a strong base together. They react together to create a weak acid and a weak base. Like you take sulfuric acid and sodium hydroxide and you mix them together. And once you have cleaned up from the explosion, you find a lot of salt, or sodium sulfate, which would help you dry up the water. But, so the equilibrium lies that way, towards the starting materials. We can call it starting materials, we can call it reactants. Stuff on it lies towards the left side of the arrow versus these are the products. And this is just, I could have drawn this reaction the other way around, that's fine, but I drew it left to right. The course is taught in North America and we're following Western convention, and so we read left to right. And so starting materials on the left, products on the right. In this case, the equilibrium lies towards starting materials or reagents or reactants. Could have seen both. I don't care. Okay, that's fine. Why? It comes down to lower energy. Things want to be in the lowest possible energy state. And a strong acid is a strong acid because it's reactive. And a weak acid is a weak acid because it's not reactive. And so on this case, we've got a weak acid and a weak base on the left-hand side. We have a strong acid and a strong base on the right-hand side. Now, this you could pull up by looking at a pKa table. That's not helpful, I think, in most of the cases. So what we need to look at is what goes into it. What determines, what makes something a strong acid or a strong base? And what determines what way the equilibrium lies. So the first thing I'm going to tell you when you're doing this analysis is you ignore, it's not quite true, but ignore neutral things. The difference in energy between neutral things is not normally very big. So I'm going to ignore that, and I'm going to ignore that, which leaves me with the two charged things. And what I'm reducing this question to basically is I'm saying, which one of those charges is more stable? We want to make the more stable charge. The charge is what's going to give us grief. It's what's causing the problem. It's what's driving a reaction is charge wants to be stabilized. So this question could be rewritten as, where is the charge most stable? It is the same question. Okay, so now I've reduced this question from an abstract question. Yeah, this is how do you know? This is what we're going to talk about now. I reduced this question from an abstract question to a concrete question over where is the charge more stable. But how do I go about doing that? So what makes for a stable charge? Okay, let's talk about that. So how can we predict acid state? Everything is about the stability of the conjugate base. If you're talking about a positively charged species, everything is about the stability of that conjugate acid. You want to stabilize the charge. The main factors are electronegativity, size, resonance, and polar effects, which is a fancy word for induction, which we've already talked about. So electronegativity. Negative charges on negative atoms is a good thing. So if you go across a row, fluoride can stabilize a charge better than oxygen, which can stabilize a charge better than nitrogen, a negative charge, which can stabilize a charge better than carbon. So if I have a choice between these guys, so if I had an equilibrium set up between CH4 plus OH minus, goes back and forwards between that and water plus CH3 minus. I ignore the neutral species, and I compare the OH minus and CH minus to say what is different. Well, one of them has a negative charge on oxygen, one of them has a negative charge on carbon. Negative charges on carbon suck. Notice they are unstable. Negative charges on oxygen are okay-ish. The equilibrium lies towards the more stable charge. Yay, stable. So in this case, electronegativity determines it. If you have it on a different atom, you see, so HF is more acidic than water. HF is more acidic than water because the conjugate base that is formed, F minus versus OH minus, F minus is more stable than OH minus. So HF is more likely to lose that proton because when it does, it makes F minus. Oh, this is what I'm, so how do you know which one's more stable? Well, you have a periodic table. This is the periodic table. Basicity goes in the opposite order. So another major factor is size. So this is up and down the periodic table. So if we're comparing HF, HCl, HBr, HI, HI is more acidic than HBr, is more acidic than HCl, is more acidic than HF. But wait a second, that's not the electronegativity thing. You just said electronegativity was important. Yeah, I did. It is important. Size is also important. So the negative charge is more stable if it's spread out over a bigger space. You know, F has this in its second quantum level. Chloride has it in its third quantum level. Bromine in its fourth. Iodine in its fifth. That's like in the 5p orbital. That's like ridiculously far away from the positive center, and that orbital is huge. So the negative charge is spread over a massive amount of space. We like spreading charge over a massive amount of space. Charge over space is a very good thing because you're not localizing the charge to one point in space. So no one spot on this iodide atom is all that negative. The charge is nicely spread out over the whole thing. So as size increases, as you go down the periodic table, things get more acidic. So H2S is more acidic than water. Which means that OH minus is more basic than a I can't actually remember what that functional group is called. It's a negatively charged sulfur. Thiolate. That's what it is. Yes. So comparing a row, you go by electronegativity. Comparing in the same column, you take size into account. Things get complicated when you need to go down a diagonal. I won't make you go over the diagonal. But if you do end up going down a diagonal, the row matters more. So things to the right, salt like S minus is more, N minus is more basic than S minus. Even though S minus is lower, the row matters more than the column. Resonance. Resonance stabilizes charge because, again, we're spreading that charge out. So this is actually exactly identical to the question we were doing. I think I actually might have a different number of carbons. I think I had a methoxide. Here's an ethoxide. And this is acetic acid. If we think of the ethoxide anion, that negative charge is all stuck on that oxygen. If we think of the acetate anion, that negative charge is split between the two oxygens. You've just decreased the density of the charge. You have spread that negative charge out amongst more people. You can think of it as kind of, lifting up cars. It's hard for one person to lift up a car, and if they actually are holding up a car, they're probably not very happy about it. And that's like holding a charge. No one really wants to hold the charge on their own. But you start getting two people in there to lift up the car. It's a kind of a light car, and they're kind of strong people. That's a lot easier than one person lifting up that car. And that's what you have here. You've got two people carrying this charge together equally. They're both a lot happier than one oxygen carrying that charge on its own. This is the final example is actually wrong. It is super stable, but it's not because of resonance. And so I'm really uncomfortable with how that is drawn, but I'm gonna leave it because it's true, but for the wrong reasons. So increased resonance increases stability of charges. Resonance is always good. The last thing I want to talk about is polar effects or induction. So electronegative substituent groups increase acidity by stabilizing charge on a conjugate base. So if we compare this, so we have acetic acid, we have fluoroacetic acid, difluoroacetic acid, and trifluoroacetic acid. So in each of these cases, when we compare what we're looking at, again, all I care about is the negatively charged species. I can't tell anything from a neutral guy. Now it suddenly makes sense when we look about this, because in this case, I've got 3 fluorines all pulling electron density from this carbon. This carbon goes, well, shit, somebody's taking away my electrons. I'm going to take electrons away from this carbon, which is great because this oxygen has too many electrons. And so this makes us pretty happy because I'm pulling electron density away from something that has too many electrons. This is quite acidic because I've got all these fluorines pulling electron density away. Here I've only got 2, so I got less of an effect. Here I've only got 1, so I have less an effect. Here I've got 0, so I don't have an effect. Everything's neutral. These guys aren't really pulling electron density away. And again, what we're doing is we're spreading that charge out. In this case here, that negative charge is partially on those fluorines. This oxygen is not carrying a full -1, or I guess a full -1/2 because it's sharing with the other oxygen. We're decreasing the weight of the electrons on all the atoms. We're sharing the electrons. Sharing electrons is good. Sharing charges is good. We want to delocalize that charge over as much space as possible. The row below, we see a smaller effect, and this is a through distance effect. So here we only have a single chlorine. Here, though, the chlorine is attached directly to the carbon, has attached to the carbon, and has attached to the oxygen with the charge. I feel like, knee bone's connected to the hip bone kind of thing. So this chlorine is pulling electrons away, which pulls them away from this carbon, which then pulls them away from this carbon, which then pulls them away from this oxygen, and everybody's happy because we're sharing some charge. pK 2.84. Still have a chlorine, but now it's 1 carbon further away, so its effect is going to be weaker because we have this through space interaction. It's going to pull less. Yeah, smaller pKa, stronger acid. So you get a weaker effect here because the chlorine's further away. We go 1 further away, the effect is even weaker. And you can see the effect still exists. Like I remove the chlorine, I get less acidic. Not by a lot, not really even by a noticeable, measurable, but not noticeable amount. And so what we have here are these inductive effects. So where I'm going to leave off today is ordering these things. The most important thing is, okay, I've got a corner up here. So because it's the most important thing, I'm going to squish it into a corner. Well, you can tell. So I got the question, does number or distance of halides matter more? Well, you can tell. The number going from 1 to 2 changed it by a whole unit. Going from 1 carbon closer to 1 carbon further changed it. Well, this changed it by a unit as well. But here that change became a lot smaller. Between, like this one changed by a unit. This one by a lot less than a unit. So generally number matters more. But space matters too. They kind of both matter. Everything matters. Everything is in balance. So the one thing you're going to hate me for, and I'm really sorry, don't kill the messenger, because it's just reality is not my fault. Like Donald Trump has a lot to answer for right now, but reality isn't really anyone's fault, and chemistry certainly isn't even his fault. All these things are in a complex interplay of interaction. And so in general, and I'm going to highlight this, in general, most important effects are atom, neg charge on right atom, and that can be either size or across the row. As we discussed, row, then column is generally the important. The row is normally more important than column. Then resonance. If that doesn't tie, if everything's a tie, you have negative charges on oxygen in both cases, the identity of the atom doesn't help you. So do you have resonance? And then induction if resonance doesn't help you. Induction is normally a much weaker effect than resonance. So that's your order of trying to work through and figuring out what is a more stable charge. We are basically going to spend the rest of the class. This is the importance of them, normally the effect they have. So the identity of the atom best defines stability. Resonance is the second best thing to define stability. Induction is kind of the tiebreaker. If it's not part of the, if it can't do resonance, resonance doesn't help. Resonance only helps if the charge is in the conjugated system. So we're going to basically spend the rest of this entire course talking about this. Because all chemistry comes down to the stability of charges and the stability of electrons. And electrons are going to try and get as stable as possible. And because and that normally means the charges are stable, because the charges are kind of they're a way that we're counting electrons. But we're really going to be focusing on trying to get the charges stable and the electrons stable, and that's everything. That's all there is to it. Because it's induction. It's pulling electrons through. So, okay, so the question is, how is chlorine stable as a charge if it isn't part of the conjugate system? It's not doing resonance here. The chlorine is pulling electrons through the carbon-chlorine bond. So that carbon-chlorine bond is not a 50-50 bond. The chlorine's got most of it. There's a dipole, which leaves the carbon slightly positive. And that carbon doesn't want to be positive, so it pulls electrons from the next carbon over, which makes that carbon slightly positive. And it doesn't want to be positive, so it pulls electrons from the next carbon over, which makes it slightly positive. Which, depending which of these examples I'm talking about, means that it could be this carbon right here, which is right next to a negative charge, and having a positive next to a negative charge is good. So the chlorine is pulling directly through the sigma bonds. It's not sharing evenly. And covalent bonds aren't evenly shared. They're polarized. Okay. A bunch of you guys have got to run off to lab. A bunch of you do not have to run off to lab, and you are the lucky ones. So I will answer some questions for a bit, and then I'm going to figure out what I'm going to do with my life. I think I have to come up with an assignment for tomorrow. So in general, more acidic equals more stable. The conjugate base is more stable of a more acidic molecule. So an acidic acid generates a stable conjugate base. If a molecule itself is highly acidic, HI is highly acidic. HI is not stable. I- is incredibly stable. But the problem is we use pKa's to measure acid stability, and that pKa refers to the protonated molecule, the neutral molecule. But to determine why that pKa is what it is, we're looking at the negatively charged species. The neutral molecule doesn't tell us why the pKa is what it is, because all the pKa is a measurement of the equilibrium concentration of the acid and the base. That is literally what it is. And so a pKa is telling us which way the equilibrium lies and how much it lies that way. And so a small number on the pKa says there is an awful lot of the conjugate base present. A high value for pKa means there is not very much of the conjugate base present. And the reason there's a lot of conjugate base present or not a lot of conjugate base present is because is that conjugate base stable or not stable? Because in all cases, the conjugate acid is H+, which it's all the same one all the way along. So it kind of gets canceled out of the equation. We don't need to think about it. We need to think about what the conjugate base is. Yeah, exactly. Anita, yes. Maybe I haven't stated that. I've been trying to say that. When you're looking at which way an equilibrium lies, you look at the charged species, you look at the conjugate base. That's what you do. Okay. I will leave it there. And I will talk to all you guys later. Good luck. Have a good lab, or not.